Hello everyone. Hi Sarang. Hi Rohi.
Hello.
Hi Rohi. Maybe we can give it a start. Let me share my screen. Give me one option. One moment. So yeah, I'll share my notepad because I just wanted to quickly revisit what we have already done on 27th. So on Monday, we just started looking into a very practical use case where we are trying to find now the rent or the price of a house. Now, and we were discussing the kind of factors which are relevant to the price of the house, which can or may no longer be limited to only one variable, right? So there may well be case that the price of the house, or maybe even a better example will be, let's say, the price of a car. Okay, so I'll just change my use case for 2 minutes and you will understand why that is the case, because I just wanted to explain a certain scenario. So let's say I am interested in the price of used cars. Okay, so I would like to buy a used car and I'm doing some analysis to understand what all are the factors, okay, that can affect the price of used cars. Okay, so this is a used car, just an example. And what kind of factors was I able to collect, let's say, as part of the data collection that I've done is, let's say, what is the, let's say, brand of the car. I'll write it as BR. What is the color of the car? Okay, if that has any effect or not. What is, let's say, the style of the car? By style I mean, let's say, whether it's a hatchback, whether it's a sedan, and so on. Yeah, so style may not necessarily include the company which has made the car, because I've already included brand, right? So I've included brand, I've included the color of the car, I've included the style of the car. Then let's say how old the car is. So let's say in number of years of age. Okay, how old the car is. So let's say if the car was manufactured and presented in for the customers in the year 2018, then the car is approximately 2 years old. So that's what I'm trying to find out over here. Or maybe I've represented the age in months, maybe how old the car is in terms of months. And obviously then I have the dependent variable, which is the price of the car, right? So all of these are uh, the independent variables, while this is the dependent variable. I'm sorry, friends. I think I'm getting a call. Give me 1 minute. I'll be on mute. Sorry, friends. Yeah. So what I was saying is this price is my target that I'm trying to find. So I'll call this the dependent variable, and this set of variables are now my independent variables. Why? Because as we have already discussed in the last session, I can no longer be using only one variable to find out what is the uh, the relationship, or how I can actually predict or approximate the dependent variable using one independent variable. That may well be possible for some cases, but it may not really be a practical use case because there are a lot of factors which can impact my outcome, right? So that's why we were looking into such kind of a setup which we were defining as multiple regression. Okay, so the earlier use case where we had a single independent variable, we were defining it as simple or single linear regression. Now we are defining it as multiple regression. You see over here, I'm not using the term linear. Okay, quite often than not, I would suggest that you should not use the term linear because it is your assumption or maybe one of the assumptions that it will be linear, but it may or may not be. There can be other cases where the regression, as we may have briefly discussed earlier, the regression might even be polynomial of this type or maybe of this type. Okay, so it may not always be a straight line, but the straight line representation is the most rigid and most easy to understand as well as explain. Hence we almost always try to validate whether a problem is a linear regression problem or not, and then whether that problem is a simple linear regression or a multiple linear regression, and accordingly we are going to take some steps which we are going to start from today, by the way. So I just wanted to quickly discuss on this some theory part of multiple linear regression because there is some consideration that is going to come over here now. And before we really start with the practical aspects, I just wanted to quickly touch base on the assumptions, on some of the assumptions and the hypothesis testing, especially of the regression use case. Also, a question that I had asked on the group, right? So now my problem is, the reason why I have just given a double quotes over here is that I'm going to write a very famous problem in this section, and this problem cannot be written over here. So I can simply take a text here and I can say multicollinearity. Okay, so what is meant by multicollinearity? Multicollinearity is a problem, and that problem can be explained as simple as, in this context, if you see, okay, the age and the price might be related to each other, which is okay, right? But can there be, okay, can there be any other variable which is affecting the age of the car, but that effect is coming from a dependent variable or an independent variable? Let's say, is the color of the car, okay, or the brand of the car impacting the age of the car, or the style of the car impacting the age of the car? Okay, maybe this is not a very good example, but let's try to imagine for some time that maybe the style of the car impacts the age of the car, or vice versa. Maybe by the age of the car, or when the car gets aged, the style of the car deteriorates. Okay, so if I have a car which is 5-year old, okay, it may have a style, it may have a current look and feel, okay, which may be overall good. Let's say I'm going to write it as good. But if I have a car which is 15-year-old, that car might really look like a very average kind of a car. Okay, if it is an average kind of a car, then obviously people will be negotiating with you very hard on the price, right? So they will really be negotiating with you very hard because now this age of the car and the style of the car are intercorrelated with each other. Okay, this is a problem otherwise known as multicollinearity. Okay, this is a very, very important problem. Okay, so I'll just select this and go to over here. Okay, so multicollinearity is a very big problem, and this is a problem that we need to resolve while we are doing the regression analysis. Please keep this in mind. If you are doing a regression analysis and there is a multicollinearity problem or intercorrelation between independent variables, otherwise known as multicollinearity, then you have a big problem, because any variation in one of the variables is already affecting the variation or change in the other variable, which means the combination of these two variables is going to inflate my expectations of price. Right? Had it been the case, I had only one variable for which I'm doing a simple linear regression, let's say, or in case of a multiple linear regression, let's say I ignored the age, I only took the first three variables. Okay, then age will not have any effect on the style, and hence I can easily and independently and very confidently try to find out what is the effect of style on the price of the car. Because style and age are interrelated, I'll have to unfortunately, okay, pick another color. And then out of these two, I have to select only one. Either I go with style or I have to go with age. I cannot go with both anymore because there is no way I can take both, because if I take both, the variation caused by both of these variables are getting summed up. Okay, and now this is causing a multiplicative effect mathematically on the price. And this is really going to be a problem. Okay, that is the reason why in multiple linear regression, this is something that I need to do. Multicollinearity should be avoided. There is no way you should never have multicollinearity. Okay. So keeping this in mind, what we would like to do now is that I'll clear all the drawings, and I would just like to explain you some things, and then I would like to quickly jump over to the implementation part itself, because there is nothing more to discuss on multiple linear regression. Everything else is exactly the same as what we have already seen in simple linear regression. Here also you have the metrics like RSS, TSS, R square, and so on. Okay, so it's the same. Okay, so the calculation, the implementation is everything the same. Now we just have to define the context. We just have to define the way we are going to do this, or the way we are actually supposed to do this, and then we can carry on. Okay, so we can clearly carry on. So before I do that, I just wanted to quickly tell you a couple of things. Okay, a couple of things that is really going to be very useful, and that we are going to write. So first of all, I'm going to write what we have already discussed. If in case of a multiple regression, okay, I'm just writing m/r. If in case of a multiple regression, just a moment, friends. Okay, so in case of a multiple linear regression or a multiple regression, if one or if two or more independent variables are correlated, even worse, they are highly correlated with each other, then they both being present in the data while we model the scenario would cause a mathematical duplicative or additive or multiplicative effect on estimating the dependent variable value. This is why basis our domain knowledge, we would need to select only one variable out of these two. Now, this is a very important and very interesting question that comes up from now and onwards. When you do practical examples, you will come to know a bit more. Even more, this is going to be a problem when you are going to do things in the office environment or in the practical environment. Because if, let's say, you have two variables, independent variables, IV1 and IV2, and these are having a multicollinearity problem. So this problem is otherwise called multicollinearity. Okay, so if we have a multicollinearity between variable 1 and variable 2, or IV1 and IV2 in a data set where you have, let's say, 10 independent variables, and IV1 and IV2 are highly correlated with each other, now comes the biggest problem. To make your stakeholders or to make your business people understand this is a challenge, because they, first of all, may or may not be from a very good mathematical background as you are, because you know statistics and probability now to some extent, and you will be researching about it, part and parcel of your role as a data scientist. But then they are not, right? So they don't understand what is multicollinearity, or what is the meaning of additive effect, or what is the meaning of, let's say, the multiplicative effect, and so on. So in that case, this gives rise to a new problem. The new problem now is which variable should I keep and which variable should I get rid of? Okay, should I keep IV1 or should I keep IV2? Because there will be half of your business analysts fighting for IV1. Half of them will be telling you, no, you should be keeping IV2. So it becomes really, really very difficult to decide. But this ultimately is going to be a joint operation only. In my view, in my experience, it is not going to be the data scientist single-handedly who is going to decide, no, IV2 goes, IV1 stays. This is not a game that we are supposed to play alone. We have to work as a team here. We need to understand the domain. We have to understand the context. We have to also understand the restrictions in the business. And we need to carefully do the selection as to whether you're going to go with IV1 and IV2. Okay, that is why I have clearly mentioned the domain knowledge thing over here. Okay, please keep that in mind. Now, let's start with the actual implementation. And before that, there are only two things that I would like to tell you. Okay, there are, first of all, a concept of hypothesis testing here as well, because ultimately, as I have already explained earlier, although considered part of machine learning only, but regression analysis is actually statistical inference, and we are going to see that right now. Okay, we are going to do a simple linear regression, again taking that iris data set of ours. We will try to find out a sample use case, and we are going to do that. And quickly we will find out that it is actually a statistical inference problem, because we will still be talking about things like F test, things that F test is something we did in case of, let's say, analysis of variance, right? And then we are going to also talk about p value and so on, right? So because this is a statistical inference test, obviously you need to define the hypothesis. And as I have asked a question on our group, it is a very simple hypothesis. Okay, there is one set of hypothesis. There is one hypothesis set. Okay, one hypothesis I can write set, because there will be a set of null and alternate hypothesis, right? So this set of hypothesis, there is one hypothesis set which is always common, irrespective of the business problem. Okay, I don't want to know what problem you're trying to solve. Okay, irrespective of the business problem, in any regression use case, the null hypothesis remains the slope of the regression line or the best fit line is 0. In other words, the value of the slope of the regression line is 0. In other words, we looked into h of theta x is equal to theta 0 plus theta 1 of x, right? So in other words, theta 1 is equal to 0. Okay, what does that mean? That means that if I have a problem statement which is something like this, and I have a few data points here and there, and I want to create a linear regression model, looking at the points only, you can understand that it is kind of a straight line which is going to fit like this. But I'm not going to do that. As per my null hypothesis, slope is equal to 0, which means my equation was y is equal to theta 0 plus theta 1 x. Theta 1 is now equal to 0, right? Then this component is gone. Y is equal to theta 0, which means the line will be this, where this value where it intersects with the y-axis, right? This is my theta 0. Hence, my null hypothesis states there is no relationship between x and y, right? In other words, y does not regress or change with any change in the value of x. As simple as it sounds, this is a null hypothesis which is common irrespective of the use case that you're looking at. Obviously, the alternate hypothesis is just going to be the opposite. The value of slope of a regression is not equal to 0, right? So this is what the common set of hypothesis is. After that, you can have specific set of hypothesis. Example given, when we were trying to predict the price of house or rent of house basis the size of the house, I can have my own hypothesis, my null hypothesis, that it doesn't matter what is the size of the house. On an average, the rent is going to be 10,000 rupees in the Pune city. Okay, that can be my null hypothesis. My alternate hypothesis is no, as the size of the house increases, the rent of the house should also increase until it reaches a saturation point. After a certain point in time, people will not be able to afford. Even if you increase the rent, it is not really going to matter. Hence, after a certain point in time, the value might go to a saturation kind of thing, but there will be a good correlation. So an increase in one results obviously in the increase of another. So this kind of a hypothesis set, I can also write it over here. Other than above, we would always define custom set of hypotheses for each problem statement. Why? Because in linear regression, we are basically doing inferential statistics, and hence we must be defining the hypothesis, because now that we are going to do practicals, okay, we are going to actually look at the F statistic, and we are actually going to look at the p-value. We are also going to look at R square, and then we come to a conclusion whether there is an inference, or whether we can accept or reject the null hypothesis. That's what we do, right? Now, before we go in, then there are at least, okay, 4, but not limited to, assumptions about linear regression. Okay, give me 1 minute, friend. Somebody is pinging me. I need to answer this guy. Otherwise, this guy is going to give me very hard time. Let me just what is he saying, man? Okay. 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 No problem. Okay. Okay. Fine. No problem. Sorry for the disturbance. I believe the screen share got stopped. Fine. So we are going to look at some very common uh, assumptions of linear regression. Okay. So the first assumption, give me 1 minute. I'm just trying to start my Jupyter notebook. Yeah, I've done that. Okay. Yeah. So let me just get back over here. Yeah. So at least there are 4 assumptions. The first assumption is there is a linear relationship between x's and y. Okay. This is the basic. Okay. When you do EDA, you should be able to find out whether there is a linear relationship. How do you find if there is a linear relationship? Using Pearson correlation coefficient, right? If you remember, when we were looking into basics of pandas, we did a data frame.corr function. Using that CORR function, we were able to get the correlation table. The numbers in each and every cell, we are going to do that right now, by the way, is giving me the correlation coefficient, and hence I am able to find out if there is a relationship or no, right? Okay, now the, give me 1 minute, who is this man? Okay. Okay, yeah. Now, the second assumption, if I have to explain, then what I need to do, let me just create a new line. Yeah. So I'll try to draw something over here, otherwise I cannot explain. So let's say this is my X and Y, very bad drawing. But let's say that I have a point over here. Okay. I have one actual point there. Okay. An actual point there. And let's say one actual point here. Okay. And now I have drawn a regression line, which is something like this. Okay, maybe my model has come up with the best fit line or the best regression line, which is something like this. Okay, now if I try and understand what is happening here, this is my actual value. Okay, this is my y actual. Let me change the color. This is y actual, so I'll call it yi, and this is my y predicted, so this is yi hat, right? In the same way, this is my predicted value, this is my actual value. Okay, this is actual. Now when I'm trying to predict, okay, when I'm trying to estimate, obviously, and in statistical terms, what usually happens is, if I'm trying to predict a value, I'm just getting rid of this red things because I am going to confuse you now to the best possible extent. When I'm trying to get, no, sorry, I should change the color. Okay, if I'm trying to predict any value, and we are going to explain this far more later on, which is happening on this point, then we assume that we have done a lot of iterations to find out this value, right? To find out this predictive value, I may have drawn, or this predicted value has come up because of a lot of lines like this one. This is the best fit line, okay, or this is the best line. To come up to this best line using gradient descent, we have drawn a lot of lines, right? Then we have selected the line where the R square is the maximum, right? We have selected the line where R square, which is 1 minus RSS by TSS, that term is the highest, right? Or we have used a gradient descent method. R square was used in the ordinary least square method, or we have used the gradient descent method where we have calculated the J of theta, the cost function, basis the value of theta 0, theta 1, right? So we have taken one of the approaches, sometimes even both, and we have found out that predicted value. That's why you can say there are a lot of values that we have come across, and then we picked up one predicted value. So we have, out of a lot of values, I have taken one value which is my actual predicted value. If you revert this diagram, this looks just like another normal distribution where you have found out one value which is my predicted value, where the cost function, okay, the cost function j was minimal, okay, was almost near to 0, or my R square was very high. So that's why we selected this as the predicted value. These distributions, or this difference, okay, is also known as error terms. What is error term? If I try to define it once more, h of theta x is equal to theta 0, which is my uh, variable that is affecting the outcome, right? And I have theta 1 x. Now I have to add another variable to make it even more practical, which is my error term. Error term is something that will come during sampling error, experiment error, setup error, environment error, I don't know. It can be introduced from anywhere. You can control theta 0 and theta 1. You can control these factors, but you can never control errors. And that is the reason why these terminologies are known as error terms. Okay, the distribution of the error term, as you can clearly see from this diagram, is a normal distribution. Okay, please note, I am not talking about x and y. X and y may or may not be normally distributed. I don't care. I don't care if x and y are normally distributed. Why? Because for me, x and y should be positively or negatively correlated for me to do a linear regression. But for me, it is essential assumption that my error terms are normally distributed. When we do the practicals by tomorrow, we will come to know why this is the case. Also, if this is the error term for this predicted value, similarly, if for this predicted value also I'll have the error term, right, or the distribution of this prediction. In that case, my third assumption, my first assumption was this line, there is a positive or negative linear correlation between x and y. Second, the distribution of the error term will be a normal distribution. What is a normal distribution? Mean is equal to 0, standard deviation is equal to 1, if you remember. Similarly, I take the normal or I take the distribution or error distribution of all the terms of all the predicted values. Here this one is the predictor value. So let's say this is E1 and this is E2, or because it is a distribution, you can also say D1 and D2. There is no relationship between E1 and E2. Okay, other than the fact that they both are normally distributed, which means obviously for both of them mean is equal to 0, SD is equal to 1. That does not mean they are equal to each other. Other than that, there is no property which is related to each other. This point is a different point, this prediction is a different prediction. Similarly, this point is a different point, this prediction is a different prediction. If that is not the case, this is not at all a linear regression use case, because then you have only single point. Why do you need to predict? If all the predictions are overlapping on top of one another, then that means that you have only one actual point, which is something like this. Do I really need to draw a line? No, right? I already know what is going to be the value of y given the value of x. Right? In this case, I do not need to do any prediction. That's why this is the third assumption. Fourth, because they are normally distributed, obviously their variance will be the same. They will have a constant variance because they are normally distributed. The standard deviation of this and standard deviation of this is the same. That is the reason why both of them are going to have a constant variance. This concept is called homoscedasticity. Okay, let me just write down what I was being talking about. The error terms are normally distributed, then the distributions of the error terms are not related to each other. Okay, x and y are, okay, x and y are related to each other, not the error terms. Okay, the error terms are normally distributed, but not x and y. X and y, the actual variables may or may not be having a normal distribution. I don't care. I am only looking into the correlation coefficient. Then the fourth one, homoscedasticity. Okay, all error terms have same or similar variance. Okay, don't worry, when we do the exercises, we'll come to know what this is and why this really matters. Okay, let me just clear the drawings. We have lesser time, it seems. Let me start a new share, which is going to be my linear regression notebook. Where did that go? I think this should be the one. I think this is the one, right? Yeah, so what I have done is I have taken this iris data set, and let's try to do something with that data quickly. And let's try, let me show you how to use some very simple techniques to calculate a simple linear regression. So to do this, let me do import pandas as PD. Okay, so I'm importing the pandas library because obviously it is a CSV file. So I'm going to read that as a data frame. That part, or the EDA part, the statistics part that we have already done, is not going to change. Okay, please don't sacrifice the data loading or data engineering part because you are doing predictive analytics. Please note this. You must always do ample amount of exploratory data analysis, because before you even think of doing any predictions, because as I've already told you, 80 to 85% of the problems will be by default resolved if you are going to have a very good exploratory data analysis methodology. Okay, okay, let me just come back here. Now I'm going to import from SciPy package. There is a module called stats. We have seen this earlier because we did the statistical test. From scipy.stats, import lin regression. I believe it is lin regress. Okay, or maybe I can do this as LR. Okay, so let me see if I have written the package name correctly or not. I hope it is. Otherwise, we are going to get an error, right? So no problem. Let me see. It should work actually. Ah, yes, it has worked. So now I have pandas as well as linear regression packages. Very simple. I create a data frame, PD read CSV, and I import iris.csv. Don't worry, friends, we are going to look at much more example. This is a baby example, and this is nothing. I just wanted to show you how to use the functions. That's it. Okay, we are going to look at much more. Okay, now Simply put, iris.corr. I'm not going to waste any time. Simply, I'm going to go to correlation. If I look at the Pearson correlation numbers, clearly, I don't have to do anything. Very clear. Petal length and petal width, maximum correlation. I don't know whether that is a positive correlation or a negative correlation. I can find that out. Okay. To do that, I can do import matplotlib.py plot as PLT, and then I can do a scatter plot, and I can find out what is the relationship, okay, between scatter plot, okay, between iris dot petal width and iris dot petal length, and then I can simply do a PLT dot show, and I can see what kind of a relationship I have. Clearly, there is a linear relationship. This x-axis is petal width, y-axis is the petal length. So as the petal width is increasing, the petal length is also increasing. Let's take this as our baby example, and let's see how we can use this linear regress function. This is just one function. We're going to look at three. Okay, this function is yet another black box function only applicable for simple linear regression. Linear regress does not apply for multiple linear regression use cases. Please note this. We already have this in our notes. Okay, don't worry. Now, the outcomes. Okay, when I call or when I execute linear regress, right? So when I execute linear regress, what it is going to give me as an outcome are four variables. Okay, first variable is slope. Second variable is intercept. Third variable is R value, or R, the value of R, not R square. Okay, it gives me R. Okay, it takes a square root and it gives the R value, and then it gives the P value. Okay, I get this four value. Fifth value also it gives is the standard error. The standard error is actually that epsilon terminology. That epsilon that I was drawing, right? H of theta x is equal to theta 0 plus theta 1x plus epsilon e. So that error term, it also gives me the error, which I was not able to calculate, but it somehow estimated it. Okay. Now to simply run this, I'm going to say LR. Okay. I'm simply going to run this LR, and then I'm going to pass the x variable and the y variable. Right. So clearly, my x variable is the petal width, y variable is the petal length. Why don't I simply do a copy paste and I do a run? I get the output. These variables slope, intercept, R value, P value, STDERR has all the outcomes. Let's look at them one after the other. Okay, sorry, I think I have done a mistake in the name. So this is the slope. Slope means what? Slope is theta 1. Is my theta 1 equal to 0? No. Clearly, I have a linear relationship. So I can be quite confident in my mind. I am on the verge of rejecting the null hypothesis. But I cannot do that without looking at the p-value. Let's go there step by step. The next thing is intercept. Intercept is how much? 1.09. So my final equation becomes, okay, my final equation becomes y. Okay, in this case, what is y? Petal length. Okay, so I'm not going to write y, I'm going to write petal length, okay, is equal to 1.09 plus 2.26. I've just taken a round, multiplied by petal width. Using this function, I should be able to estimate any value of petal length given I have the petal width. Okay, that's exactly what I could do right now. Okay, again, let's look into the rest of the variables. Next value is R value. Okay, but do I really need the R value? No, I need R square value. So I'm going to do a square. I get the R square value 0.9269. Is this closer to the correlation coefficient? Somewhat, but it is not equal. This is a very important learning. R square should not be confused with correlation coefficient. Correlation coefficient was 0.96. R square value is 0.926. Also, correlation coefficient was positive, hence there is a positive relationship. R square is always going to be positive because its range will be 0 to 1. Correlation coefficient can even be negative, right? Next value, p value. P value is 5.78 approximately, e to the power minus 86. So this is like 10 to the power minus 86 multiplied by 5.78. So this is very, very small. And obviously, p value in this case is very small than 0.05, which is my acceptance, right? My confidence interval, because I've not specified anything, is 95%. And that's why my alpha value is 0.05. P value is less than alpha. I reject the null hypothesis. Okay, I have got all the outcomes. We don't have time now. Let's make a close here. We are going to continue tomorrow and look at a lot more. Okay,
Thank
thank you
you.
so much. Good night.